to know, the directional derivative of the function in the direction of a certain unit vector u. So also at AB, well, there is a way of calculating this. Do you remember the rule? What it is exactly? The directional derivative of f in a direction of a vector u. Any idea? How do we calculate this vector? The directional derivative. Anyone? Yep. Yes, it's actually fx at AB multiplied by u1 plus fy at AB multiplied by u2. That's one way of looking at it. The other way is to say, in fact, it's the dot product of the gradient with the unit vector u. Yeah. So it's this, this, exactly the same thing, and this will give you the directional derivative of this function. And of course, we know that in general, when you have a dot product like this, you can write it as the magnitude of the first vector at AB. This is AB. Multiplied by the magnitude of the second vector, multiplied by the cosine of the angle theta between the vectors. So another form of writing this directional derivative. Yeah. So the magnitude of the gradient multiplied by the magnitude of the unit vector multiplied by cosine theta. Finally, what is the magnitude of the unit vector? What is this number here? What is the magnitude of u? What is the magnitude in general? If you take a unit vector, what does it mean about its magnitude? One, yeah, it's equal to one. Yeah, this is equal to one. So in general, the directional derivative, yeah, of a function, the directional derivative of a function f in the direction of a unit vector u, you can write it as the magnitude of the gradient multiplied by the cosine theta, where theta is the angle between u and the gradient vector, like this. Now, from here, let me just give you this simple question. Suppose you have a function f of x, say, equal to 5 cosine x. What is the maximum value of this function? 5 cosine x. 5, yeah? 5 will be the maximum value. What is the minimum value? Not 0. Yeah. Remember, cosine x is between, yeah, it's minus 5, yes. Cosine x between minus 1 and 1. So when it is 1, you get 5. When it is minus 1, you get minus 5. So a function like this, its maximum is 5, its minimum is 5. So if I give you this function here, look at the directional derivative. What is the maximum value of this directional derivative? What is its maximum value? Well, it's going to be this number here. That's the maximum possible value for the directional derivative at AB. So here this leads us to the following theorem. So let me go to it, and yeah, okay. So, suppose you have a function f differentiable at a point AB, then the maximum rate of change of f at AB is the magnitude of the gradient. And this occurs in the direction of the gradient. That means this happens when theta is equal to 0. Like u and the gradient are in the same direction. So that's the maximum rate of change. So it's equal to the magnitude. If they ask you to find the maximum rate of change, that means you need to find the magnitude of the gradient function. The minimum rate of change is minus the magnitude of the gradient, and these are important things that you need to remember. So here is a question. Find the maximum and minimum rates of change of this function at the point 1, 3. So let's find this. So I want to find the maximum rate of change. That means I need to find the gradient. So find fx. What is fx? What's the derivative of this function with respect to x? 2x, yes. So that means the function fx at the point 1, 3 will be 2. And then you find fy. Also, fy is 2y, yeah? 2y. So that means fy at 1, 3 is going to be what? 6. Okay, good. That means the gradient of our function at the point 1, 3 will be the vector. What vector? So the gradient of the function f at the point 1, 3 is the vector 2, 6. Okay, great. The vector 2, 6. So this means the maximum rate of change you want the maximum rate of change, you need to find the magnitude of the gradient. That's it. So it's going to be the square root of 2 squared plus 6 squared, and this will give you the square root of 40, which is 2 square root of 10, and this is the maximum rate of change of this function. So this function is changing around the point 2, 3, 1, 3. It is changing when you move in different direction. The maximum rate of change is 2 square root of 10, maximum. Now, what is the minimum rate of change? Minus, that's it. That's it, yeah. Minimum rate of change will be minus 2 square root of 10. That's it. Like this. So at the point 1, 3, which is somewhere here, our function is changing when you go to different directions. It's changing. Well, the maximum change, rate of change is 2 square root of 10, and the minimum is minus 2 square root of 10. Are we okay with this? So you want to find the maximum, minimum rates of change, just find the gradient and the magnitude. So find the gradient of the function, and then you find the magnitude of this gradient. That will be the maximum rate of change. Okay, so that is the idea of 1 and 2. Now, 4 is also an important thing. I want to explain this point number 4. Yeah. By looking at an example. So this 4 says the gradient vector at the point AB is orthogonal to the level curves f of xy equal to c at the point AB. Okay, so let me explain what we mean by this. Suppose you will understand this fairly quickly, I hope. Suppose you take x squared, the function x squared plus y squared. So, and I consider one level curve of this function. That means x squared plus y squared equal to a constant. Let's say we take a constant 4, yeah? Like this. What is this level curve? If I want to graph it, what is it? It's a circle, yeah? Circle centered at the origin, yeah? With a radius of, what's the radius of this circle? 2, yeah? 2 minus 2 minus 2, 2, like this, yeah? All right. Now, take a point on the circle. So, for example, I consider the point square root of 2, square root of 2, which is on the circle. It's somewhere here. Yeah. How do I check, by the way, this is on the circle? How do I check that this point is really on this circle? You substitute. Yes, substitute. X is square root of 2, y is square root of 2, and you will see that it will give you 4. So yes, it is on the circle. Now, on this, at this point, there is a tangent line, yes? There's a tangent line. So, yeah, we have a tangent line like this. Now, what this part, what the theorem says is that at that point, the gradient vector is exactly normal. So square root of 2, square root of 2. The gradient vector is normal to this tangent line. It makes an angle of 90 degrees with the tangent line. So the gradient is always perpendicular to the tangent, like this. So that is what part. So at every point, at any point, the gradient is always like this. It always makes an angle of 90 degrees with the tangent, like this. So every point, the gradient will be orthogonal or perpendicular to, yeah, this is what this is telling us. Part 4 says that the gradient is orthogonal to the level curve at the point AB. It makes an angle of 90 degrees. So that is what this number 4 point is telling us. So that gives us an idea about the gradient. It's basically a vector orthogonal to the surface. Okay. Now, I will not do 6.6. I want to. Now, here is the last part, basically, of this section. Is quite important. Suppose you have in 3 dimensions now, you have a function f of 3 variables. you have a level surface, fxyz is equal to k, where k is a certain constant, then the equation of the tangent plane is given by this long equation here. So let me perhaps try to explain what is happening here. Okay, yes. Okay, so you have a function f of x, y, z, yeah, equal to a certain constant like this. Let's say we have x squared plus y squared plus z squared is equal to, let's say 9, yeah, like this. Let's take a look at this example. What is this surface? What is this surface? If I want to graph it, what is its graph? It's a sphere, yeah? Yeah, it's a sphere, yes, of radius 3, like this. Yeah, okay. So take a point on the sphere, take a point anywhere on this sphere. At that point, there is a plane which is tangent. So this is the tangent plane. To the sphere at this point ABC. Can you imagine this? Yeah, you have a sphere, take a point on the sphere, and at that point there is a tangent plane here. Now, what I want is to find the equation of this tangent plane. How do we get the equation of the tangent plane? Now, do you remember what do you need to have to write the equation of a plane in general? If you want to write the equation of a plane, what do you need? Do you remember? Okay, yes, you need the point which we have, which is ABC. Yeah. So we have a point ABC here. It's okay. It is given to us. What else do we need? Other than the point, what else do we need? The normal vector. We need the normal vector A, which we called A, yes? So you need the normal vector. Well, in this case, the normal vector is actually the gradient of the function. We know that. The gradient is normal to, so the normal vector is basically the gradient vector, which is fx at ABC, yeah, ABC, fy, and also fz, like this. So we have the point, we have the normal vector. Now we can write the equation of the tangent plane. You may remember it's going to be A1, which is fx at A, B, C, multiplied by x minus A, plus fy at A, B, C, multiplied by y minus B, plus fz at A, B, C, multiplied by z minus C, all of this equal to 0, and that is the equation of the tangent plane to the surface f x, y, z equal to a constant c, like this. So that is basically what we have here. So you want to find the equation of the tangent plane. Well, you can do it using this formula, and this is what is given here. It's exactly what is given in this formula here. So let's see. So this is really important. We need to have a look at how it works through an example. So find the equation of the tangent plane and also the normal line. I will come back to the normal line in a moment. So here is the surface, and I want to find the equation of the tangent plane to this surface here. Okay, now, according to this rule, look at it carefully. So what do we need to find? First, do we have A, B, C? Do we have A, B, and C? Yes, we do, yeah? What is A? 1, yeah? Y is 2, and C is 3, yes? So we already have that. So A is 1, B is 2, C is 3. Now, according to the equation, look at it. What do we need to find now? What do we need to find? Fx, exactly. So we need to find Fx first at x, y, z, and then at 1, 2, 3. So we need to differentiate this function with respect to x. So what will it be? So 3x squared y, yeah. And then that's it, huh? That's it, I think. Yes. So fx at 1, 2, 3 will be what is it? 6. Okay, great. Number 2, I want now the partial derivative with respect to y. So what is this? X cubed, good. X cubed minus 2y. Again, I want this at the point which is 1, 2, 3. So substitution. And this time, minus 3. Thank you, Noor. Yes. Okay. Finally, 3, I want fz, xyz. It's 2z, huh? 2z. Yes. And therefore, fz at 1, 2, 3 will be 6. Okay, great. Now, can we write the equation of the plane now? Can we write the equation of the tangent plane? Yes, we can, huh? Yes. So, the equation of the tangent plane is 6 times x minus 1 minus 3 times y minus 2 plus 6 times z minus 3 equal to 0. And we have the equation of the tangent plane to the surface at the point 1, 2, 3. Are we okay with this? Yes? Yeah? Okay, good. Now, so this is the plane. We basically, it's our plane. It goes through the point 1, 2, 3. Yeah, this point 1, 2, 3. Its equation is here. Now, the other thing that they're asking us, what are they asking us to find also? If you read the question, what is What do we need? The normal line. Yes, exactly. So what we want is the equation of the normal line. So what do we mean by normal line? It's the line which makes an angle of 90 degrees with the plane. Yeah, like this. Yeah, 90 degrees. So normal line. Now, of course, we know that the gradient vector itself makes an angle of 90 degrees with the plane. So now I want to again try to remember, what do we need to, if you want to write the equation of a line in general in space, what do you need? You need a point, good, yes, and the vector, yes, the vector in the same direction as the line. And we have this, we have both of these. The point is 1, 2, 3, and the vector is the gradient vector. Yeah. So at 1, 2, 3, which is, yeah, the gradient vector, it's 6 minus 3, 6. Now, using these two things, we can write the equation of the line, no problem at all. We have the vector and we have the point. So the equation of the normal line is, remember, they are parametric equations. Yeah. So x minus 1 equal to 6t. You remember that? Yeah. What's the second equation? What's the second equation? Y, yeah, y minus 2 is equal to minus 3t. And finally, z minus 3 equal to 6t. And that is the equation of the normal line. Yeah. And of course, if you put t equals 0, you get the point 1, 2, 3. Other values of t will give you points on the line, along the line, wherever there may be. So you will be getting points on this normal line. Are we okay with this? So, important question, this one. You really need to know this. You will probably see these questions like this in various places, tests, assignments, and so on. So finding the equation of a tangent plane and the normal line for a certain surface, very easy, no big problems here at all. You find the partial derivatives, then you write the tangent, the equation of the tangent, and you can write the equation of the normal also using the partial derivatives. Right, so that is basically this section. Let me continue with some of these exercises. We did, of course, we did this. Yeah, 5, we did it. 7, I will leave it to you. You can do that. Now, in question 11, we want to find the directional derivative of f being this function, at the point 2, 1 in the direction of this. So this is the function. This is the point. And this is the vector. You can check that this is actually a unit vector by finding its magnitude, and you will see that the magnitude is 1. So we have this. So I want to find the directional derivative of f in the direction of the vector u. So that is at the point 2, 1. So what do we need to find here, girls? What is the... so how are we going to get this directional derivative? Yeah, we need to find the partial derivatives, fx, yeah? So let's do that. So number one, you need to find fx first at xy, any point. What is f of xy? Fx, the derivative with respect to x, it's 2xy, yeah, thank you, yeah. So this means fx at the point 2, 1 is 4, huh? It's going to give us 4. 2 times 2 times 1, it's going to be 4. Then you need to find the fy. Fy, what is fy, girls? Anyone? Yeah, it's going to be x squared, yes, plus 8y. Good, thank you, thank you. And then we need, of course, that at the point 2, 1. So substitute. And it's what, 12? Is it 12? Yeah, 12, yes. Okay, good. Now, okay, so let me just this. Okay, so therefore, after that we can write, so, yeah, the directional derivative of f in the direction of u at the point 2, 1 is going to be 4 times what? So we need this, yeah, this number, and this number. So 4 times half, yeah, plus 12 times square root of 3 over 2, and you calculate all of this. So it's basically 2 plus 6 square root of 3, and it's something like this. So possibly around 10 or 11 perhaps here. If you calculate it, yeah, possibly, yeah, 12, yes, okay, 12.4. That's fine. Okay, good. So that is basically this one. Now, here, again, directional derivative. Here is the function. Here is the point. And here is the vector. The vector is 3 minus 2. Now, in what sense is this question a little bit different from the previous one? Why is it a bit different? This question is a bit different from the... Yes, here, this vector is not a unit vector. Yeah, this is not a unit vector. So therefore, your first step, yeah, first step here is to find the unit vector. So u will be 1 over, yeah, so here is the vector v. So you need to find the unit vector in the direction of the vector v. So it's going to be 1 over, what's the magnitude of the vector here? Square root of 13, yeah? Multiply by 3 minus 2. So the unit vector is 3 over square root of 13 minus 2 over square root of 13. So that is our first step. Now, once we have the unit vector, then we need to go into, what do we need to find now? Thank you, Nora. Yes. So we need to find fx and fy. Yes. So fx at the point xy in general, you can differentiate that, and I will give you the answer. It's up. You can check it. It's x over square root of x squared plus y squared. You can check that. So that means fx at the point 3 minus 4. So substitute, and you will see that it's 3 over 5. In the same way, we can find fy. Yeah, you differentiate the function, you will find y over square root of x squared plus y squared. So that means fy at the point 3 minus 4 will be minus 4 over 5. And now we have all the 4 numbers that we need to find the directional derivative. So the directional derivative of f in the direction of the unit vector u is going to be 3 over 5 multiplied by what? Can someone help here? So the directional derivative, 3 over 5 multiplied by u1. What is u1 here? The first component, yeah. 3 over, yeah, thank you. Yes, 3 over square root of 13, and then plus the minus 4 over 5 multiplied by minus 2 over square root of 13. And you do these calculations, and you will see, yeah, you can complete that and see what happens. Okay, basically it's the first one will give you 9 plus 8, so it's 17 over 5 square root of 13, like this. Okay, good. So that's fine. I will leave the rest. Yeah, I will leave you 15 and 7, 19. You can do them exactly the same way. Here, yeah, find the directions of maximum and minimum change of f and the values of the maximum and minimum rates of change. So there are 4 things we need to find. First, the direction of maximum rate of change. Well, the direction of the maximum rate of change is just the gradient vector. So when we move along the gradient vector, this is where the function changes the most, with the maximum rate. So we need to find this. Okay? So you need to find the gradient at the point 2, 1. So let's find that. fx is 2x. So fx at 2, 1 is going to be 4. Fy is minus 3y squared. So Fy at 2, 1 is what? Minus 3? Okay. So therefore, the direction of maximum rate of change will be given then by 4 minus 3. That's it. So that's the direction. It's the gradient. So really important this. The direction is of maximum change is the gradient. Direction of minimum change is minus, yes, minus the gradient. Minimum rate of change, so please memorize all of this, is minus the gradient. So it's basically the other direction. So it's going to give you minus 4, 3, like this. Direction of minimum rate of change. Number 3, now we want actually now the maximum and minimum change. The values of the maximum and minimum rate of change. So maximum rate of change is the gradient and its magnitude. So maximum rate of change, the magnitude of the gradient. What is the magnitude of the gradient? It's 5, yes, exactly. So it's the square root of 4 squared plus minus 3 squared. So it's going to give us 5. And finally, the minimum rate of change will be minus the magnitude of the gradient. So it's minus 5, yes, exactly. So minus 5, that's it. So we have, if you want, the 4 answers. They're all here. Please, here you have to be a bit careful. If they're asking you for a direction, the answer will be a vector. Direction means a vector. But the maximum rate of change is a number. It could be positive, it could be negative. So maximum rate of change is the magnitude of the vectors that you found over there. So please be careful about these things. Yeah. So you need to pay attention to what they're asking you to find. Okay. So all of this really not very difficult. If you focus, you concentrate, it's going to be fairly simple. All right. Now, maybe the last question here is an example of finding the equation of the tangent plane and also the normal line, yeah, to the surface at the given point. So we have x squared plus y cubed. Z is that. At the point 1 minus 1, 0. Okay. So you need to change this into, we can change this equation into x squared plus y cubed minus z equal to 0. Like this. Okay. Now, at the point, yes, at the point 1 minus 1, 0. So I want to find the equation of a tangent plane. What do we need here? What do we need? Yeah, fx, again, you can see that they're really important, these partial derivatives. They come, they're always there. So we need the fx, yeah. Here, it's going to be 2x. So fx at the point 1 minus 1, 0 is going to be 2, yeah? And then you need to find fy, which is 3y squared. So fy at 1 minus 1, 0 is going to be 3. And finally, fz, which is minus 1. So fz at 1 minus 1, 0 is minus 1. So can we write the equation of the tangent plane with this? Do we have enough information to write? Yes, we can, yeah? So, yes. So that means the equation of the tangent plane will be 2 times what? 2 times x minus 1. Thank you. Yes. And then plus 3 times, yeah, y plus 1. Great. And then, yeah, minus z, yeah? Minus 1 times z minus 0. So the whole thing will be minus z equal to 0. And that is the equation of the tangent plane at the point 1 minus 1, 0. Now we need to, is that the end of the question? No, yeah, we need something else, yes? We need the equation of the normal line, yes. So now we need the normal line, which will be y minus, why am I starting with y? X, yeah, minus 1 equal to 2t, yes, very good. And then y plus 1 equal to 3t, thank you. And finally, z equal to minus t, and that will be the equation of the normal line to the surface. Okay, so that is this section. The next question, by the way, 43, very similar to this one. You can try it. It's a really good practice for you to do these questions here. Now, any questions at all here? I understand these sections that we are doing at the moment, they are quite heavy. There are a lot of stuff there, but with practice, with some reviewing, it should be fine. Yeah, because every question has its own way of being solved. You may have to 2-3 steps, and you should be able to get the final answer. Any questions at all regarding this? Anyone has a question? No questions? All right, great. So I will take a 5-minute break. I will close this section and we can come back and to a new section in a moment. So take a small break and back in a moment. Thank you.